Okay, in this video we're going to continue the example from the last one that we were looking at with the red and blue drink. So you might remember that the initial state of that was 50-50. So 0.5 was blue and 0.5 was red. We had a transition matrix that we'd made up, which was 0.6, 0.4, 0.7 and 0.3. This was blue, red, blue, red. This is from, and this is to. Okay, and we worked out that after one transition, after 1 month, that was the time period we were looking at, the state of the system after 1 month was the transition matrix multiplied by S0. We also saw that the state of the system after 2 transitions was the transition matrix multiplied by S1, which, by the way, we had worked out was 0.635 and 0.365, where this was blue and this was red. Rather than having to work out the state of the system after 2 transitions, by having to go through working out S1, because you imagine if we had to work out the state of the system after 20 transitions, then S20 we would need to go the transition matrix multiplied by S19, but that would mean we'd need S19, which would mean we'd have to have done S19 equals transition matrix times S18. And so on. We would have had to do a lot of calculations. But let's have a look and see how we could do this quicker. Really what's happened here is to go from S0 to S2, the transition matrix has had to operate once here and then again here. So the transition matrix has had to be applied twice to go from S0, what we started with, through to S2. So let's have a look at an alternate way. We could go S2 is equal to the transition matrix operating twice, means effectively you're going transition matrix times S0, which in matrix terminology we would write T squared times S0. Now if we get our calculator and try that, remember our transition matrix was actually matrix A, so we'll go matrix A squared multiplied by matrix, and I put my initial state into matrix B, alpha B, equals, and I'm not sure if you can see on my screen there, you can see that we get exactly the same value, the 0.635 and the 0.365. Okay, so we could generalize this then and say, well, we don't actually have to go through all the individual transitions, going from S0 to S1 to S2 to S3 and so on all the way up to S20 if that's where we wanted to go to. We could say that S20 equals, think about it, what would it be? How would we go straight to S20 from S0? Well, really, to get to S20, we've got to have the transition matrix operating 20 times. 20 different transitions. 20 different transitions. So, in our calculator, then that's really easy. We can go, we can even go and edit the one that we had. Matrix A to the power of 20 multiplied by matrix B. And we get 0.6363 and 0.3636. as the state of our system after 20 transitions. That is, remember this was blue, this was red. In other words, 63.63% after 20 months like blue, and 36.36% after 20 months, this is, like red. Well, what about after 50 months? What's happening after 50 months? So let's go back and change it and see what happens if we do 50 months. In other words, S50. Let's try S50. S50 would be after 50 transitions, so t to the power of 50 times our initial. And lo and behold, we get 0.6363 and 0.3636. What do we notice? The state of the system after 20 months and the state of the system after 50 months hasn't changed. So even though some drinkers are still swapping, some red drinkers still go to blue and some blue drinkers still go to red, we say that the system has reached a steady state. Steady state meaning the proportions are no longer changing. And this is a really important point. And we can say at steady state, the state of the system is equal to the transition matrix multiplied by the state of the system. Which is quite interesting because here we've got S is the state of a system. It's a column matrix. A column matrix is equal to some other matrix times that column matrix. In other words, at steady state, this transition matrix doesn't change S. Another way we could write it more generally, we could say that XY is equal to the transition matrix multiplied by XY. In other words, the transition matrix doesn't change the values of X and Y at steady state. Now there's an algebraic way we can also work out the steady state, but for now we'll rely on the numerical method. So in future, we just tested the state of the system after 20 transitions and after 50 transitions, and we saw that it didn't change. That's how we knew it was steady. But if it would be incorrect of us just to jump straight to 50 transitions and assume it's steady. You really need to test two values and show that it doesn't change between those two values. Most of the time it'll be well and truly steady after 50 transitions. So I suggest you try 50 transitions, and you could also try 51 or 55. But try two different numbers, two different values for the transition matrix, and show that the values, the state of the system doesn't change. So, just repeating, the steady state of the system is when S is equal to TS. In other words, the transition matrix leaves those values unchanged.